All right, so I'm very happy to be in Korea for the first time, and I'd like to thank Joe and Marshall for arranging this conference and the opportunity to speak. I'm not really a very dynamic person, so usually I study static problems and the calculus of variations, but because this is a conference on nonlinear conservation laws, I thought I would talk about a kind of long-standing project that I have going on with Herbert Koch and Jochen Denzler to understand the higher time asymptotics of the past diffusion equation. So it also seemed appropriate because this is the problem that I worked together with Yongjong on about 5 or 6 years ago. So the fast diffusion equation, it's a nonlinear kind of heat equation that models the diffusion of a non-negative density on Rn. And I can write it in several different ways. Laplace of rho to a power m. Or I can take one of the derivatives and have, or I can write it in the form of a conservation law for a density being driven by a pressure, in which case I would have divergence of rho gradient of, and this would be the pressure here. So when n is larger than 1, this model is used to model things like a fluid penetrating a rock or a population spreading, in which it's called the Poisson medium equation in that regime. A population spreading by kind of a diffusion process, except the rate of diffusion would depend on the local density of the population. So when m is less than 1, it's used to model things like curvature-driven flows and avalanches and sand piles, so geometric evolutions. And so when Richard Hamilton talks about this equation, he describes it as the bunny rabbit equation, borrowing from this kind of model. And he says, well, the way you should think of it is that you have some initial density of rabbits, rho naught, and at each position x, what happens is the rabbits look around and they run in the direction of decreasing pressure gradient, and they run with a speed proportional to the density. And so if m is larger than 1, then the speeds are lower at low densities and higher at high densities. And in that case, you can get things like if the solution is initially compactly supported, it stays compactly supported, unlike the linear heat equation where it would immediately develop exponential tails. But in the case that I want to talk about today, the fast diffusion equation, it's the opposite regime, where the rate of diffusion is low at high densities and high at low densities. And so close to a place where you have 0, you have very rapid diffusion. And so instead of you immediately develop long tails, and they're not exponentially decaying anymore, they're algebraically decaying. Sorry, m? M could be negative, but for the purposes of today's talk, it won't be. So this would be after some time, you might see something like this. And so this thing has a characteristic width. And in the case of the heat equation, it would be like tau to the 1/2. And in the case of the nonlinear equations, there's a correction to this 1/2, depending on the nonlinearity, m. And so I actually prefer to think, so I prefer to write for what you call it esoteric reasons, I prefer to think of m as being something of the form 1 minus a correction depending on the dimension and power p. And so the rate of spreading depends on p. And if the linear heat equation is the case p equals infinity, and then you have exactly tau to the 1/2. And another way to interpret this this guy p is that the thickness of the tails, rho x tau at some positive time goes like a constant depending on tau x to the n plus p as x goes to infinity. So this nonlinearity also determines the thickness of the tails. And so much in the spirit of Joel's talk this morning, the idea is that when you have this kind of evolution, it sort of forgets the initial conditions and it evolves towards some self-similar solution. In the case of the heat equation, that would be the Gaussian heat kernel. And in the case of the nonlinear diffusion equation, it's some analog of that. But so the first thing that I'm going to be interested in is what is the rate of forgetting. And so the idea is that no matter what compactly supported initial data I start with, I might as well normalize this to B1. After some time, what I'm going to see is some spreading characteristic self-similar profile spreading at this rate. And so for example, in the case of the heat equation, you can measure this forgetting in various different norms. You have the heat kernel here, and for example, you can look at the L1 norm, and then that will go to 0 as tau goes to infinity. And in the case of the nonlinear diffusion equations, if you take any two solutions, and look in the L1 norm, then this goes to 0 as tau goes to infinity. And this was first shown in the porous medium regime by Friedman and Kameen. Their argument also extends to the fast diffusion regime as shown by Vasquez in about 1983. And I should say, well, there's a little problem about the thickness of these tails. So if the tails become too thick, then mass can leak out at infinity. But as long as p is bigger than 0, then mass will be conserved. And notice that's exactly what you need for integrability of this tail in Rn. And so I will always be interested in the case that m is bigger than m0, 1 minus 2 over dimension. And lots of people in recent years have been interested in quantifying rates like this. And so let me call this exponent here beta, this exponent. And so around 2000, 3 different groups of authors, Carrillo and Pascani on the one hand, and Dolbeau and Del Pino, and also Felix Otto, were able to show that you have decay like this if you start with compactly supported initial data. And this decay rate, so let's see, without a rate, these results were true all the way down to m equals, I guess, m0. And this decay rate holds if m is bigger than mn.
Is that sharp?
It is sharp. And it's sharp for the following reason. Well, okay, so it's sharp in this range. And it's sharp because if I take the spreading self-similar profile and a translate of that spreading self-similar profile, and I compute the rate, the L1 difference between the two of them, it goes down to exactly this rate. And of course, there's another conservation law in this problem, which is as long as I'm bigger than m1, so this distribution has first moments, it's also true that the center of mass will be preserved by the evolution. What should I say? Equals interval x rho naught. And so you might be able to improve this rate by putting the center of mass at the origin. And various people have done things like that, starting in the radially symmetric case by Carrillo and Vasquez. We're able to improve this to rate 1 over tau for radially symmetric data. And then without the radial assumption, Yongzheng and myself were able to do this in a certain range of m between I guess, m0 and m2, I think. And Slepchev and I were able to show 1 over tau by putting the center of mass at the origin m was bigger than mn, actually we were only able to show 1 over tau to the beta minus 1. 1 over tau to the 1 plus epsilon. I mean, we weren't quite able to get to 1 over tau, but almost.
Why did they use the L1 norm?
This is an excellent question. And it's germane to things that I want to say. Let's just say it's convenient. This was one of the first things people looked at. So people also looked at decay in other senses. E.g., there are various Lyapunov functionals associated to this evolution, and you can ask how fast does the Lyapunov functional tend to its minimum. And another form which is going to be very germane to what I want to say is relative L infinity. So let me first say that if you put integral of x rho non equals 0, this could actually be improved to 1 in a very large range of n. So let's say m less than 1 and not equal to m minus 2. And that result was recently shown by a group of 4 authors, Bonfort, Grillo, Dolbeau, and Vázquez. And actually they have several papers on this topic, and one of them includes Adrian Blanchet as well. Okay, so but actually this turns out not to be strong enough for saying much about the higher order asymptotics. So a notion that's more germane to what I want to talk about is what I call relative L infinity, and that's where you look at rho 1 of tau y minus rho 2 of tau y, and you normalize by one of them. Let's say rho 2. So this was shown to tend to 0 as tau goes to infinity, and this is for m between 1 and m naught. And this was the result of Vázquez, 2003. And so one of the first results to come out of our work is that this can actually be improved to this rate here. Let's say m bigger than m2. But really this is just the starting point for me, because what I'm really interested in is what happens when we go beyond the first order. So it would be very nice is to be able to say that rho could be approximated by a sum of a bunch of things. And somehow that's the kind of thing that people do for in a finite dimensional context using the methods of dynamical systems. And so the idea would be that if you have an evolution of the form x dot equals f of x, for example, for x in Rn, let's say, and if this has some fixed point, f of x infinity is 0, then you want to try to linearize this dynamics and say, well, x minus the fixed point, the evolution of that should be governed by the eigenvalues of the derivative of the vector field, and then there would be corrections. And so several things to point out about this, but so in order to do this kind of thing, you need some smoothness. And so when you try to apply ordinary, dynamical systems methods to partial differential equations, you run into a lot of trouble, because having smoothness results in Banach spaces is much harder than having smoothness results in finite dimensional spaces, and questions of choosing the topology become very delicate. And one of the problems with this evolution here is that where rho tends to 0 at infinity, the evolution is degenerate. And so it's not as, the ellipticity, the parabolicity of the equation is degenerate. And so things are not as smooth as you might like. So need smoothness. And we got stuck on this point for a long time, sort of finding the right Banach spaces to try to do this in. So actually this evolution is known to be to have a gradient flow structure, since the work of Felix-Otto was, yes. And something else I should say. So what did I want to say? I wanted to say the time asymptotics ought to be determined by the eigenvalues of this operator here. And of course, as it stands, the spectrum of this thing is continuous. And so you don't learn much from eigenvalues. And the point is that as I've expressed it, the dynamics are not exponentials in time, they're polynomials in time. And so it's good to do a rescaling of time if I want to find some exponential rates. And it's also good, this red thing is spreading at some characteristic rate. And so if you want the dynamics to have a fixed point, like this one, it's good to view this evolution from a receding reference frame. So if you watch the picture from this distance away, then the evolution will indeed tend to a fixed point, in the same way that when you want to prove the central limits theorem, you need to rescale by the number of things, by the square root of the number of things that you've added up if you want to see it converge to a Gaussian. And so what's the rescaling that I want to look at? Right, so let's relate u rho to a new function u, and I want the new time to be related in the logarithmic way to the old times. The new time will be like log of 1 plus 2b tau. And I want to view the evolution from this distance away. So let me also divide y by 1 plus 2p tau to that power. And I want u to have the same amount of mass as rho, so let me put the right factor outside to conserve mass. And so if rho satisfies the original evolution, then u is well known to satisfy the evolution that looks just like the one we had before, except now there's this rescaling term. And now u is a function of x and t. And so this new time gives me some hope of getting exponential corrections here. And the observation of Felix-Otto was that in fact this rescaled evolution has a gradient flow structure as well. So it's something like x dot equals minus grad h of x. And so df will be Hessian of h at x infinity. And what Densler and I did already a number of years ago now was find the linear spectrum of this operator here at the fixed point of this evolution. So I guess this would be the moment, huh? So this evolution here fixes exactly this density here, and that's the density that plays the role of Gaussian in this problem. You see it has the right decay at infinity because it has exactly t moments in dimension n. And the constant p, which stands for Barenblatt here, because this solution was discovered by Barenblatt 50 years ago, This is also a normalization constant which can be used to select mass 1. So as I was saying with Euclidean density, we found the spectrum of the Hessian of the energy at this fixed point. Let's call it UV. And we found that it consisted of a number of eigenvalues. And some continuous spectrum. And so I can tell you what the eigenvalues and the exact values, if you like. Lambda LK is L plus 2K times P plus so I hope I got it right.
Why do you index the eigenvalues with two parameters?
So this is like quantum mechanics, right? This is a radially symmetric potential. And so when I do linearization, I get an angular part and a radial part. And L is sort of an angular quantum number, and K counts the radial modes. And because the angular part has multiplicity, these eigenvalues also have multiplicities. And right. Oh yes, plus NL. And for any finite value of P, except for P equals infinity, which is the heat equation, I have this continuous threshold. I have only finitely many eigenvalues below the continuous threshold, and then I have also finitely many embedded in it. And actually, so you don't really have all L and K, there's some constraint. L plus 2K has to be less than something depending on P. I don't want to remember right now what the constraint. So there's finitely many of these. And then there's this continuous stuff.
How did you calculate them exactly?
With hard labor.
Okay.
So the answer is that after you do the separation into spherical and radial variables, the radial equation turns out to be solvable in terms of hypergeometric functions. And okay, so what's the update? So far I've been describing work that's several years old, and the update is that we're now able to make some rigorous statements about what the relationship between these eigenvalues which govern the dynamics of the linear problem is in the actual nonlinear evolution. And this turns out to be more delicate than one might have expected. So let me say a few other things. So one of the problems is this question of smoothness in Banach spaces. Another problem is that, so what am I expecting? I'm expecting to see something like x minus x infinity is like a sum of some eigenfunctions times some eigenvalues, and maybe with some coefficients. And so I would expect decay terms like these eigenvalues that are occurring here. But that's if I neglect the quadratic stuff and the higher order stuff. And so if you plug this ansatz back into this equation, you ask whether it's self-consistent or not, you see that at the quadratic level, what you start to get are terms like e to the minus 2 lambda 1t and e to the minus lambda 1 plus lambda 2t, and so on. So this is a well-known phenomenon, and it's, I think of it as being a little bit like when you play a musical instrument, you don't hear only the fundamental frequency, you also hear overtones. And so these guys are like the overtones that come from the quadratic and higher order corrections when you do analytic dynamical systems. If some of the eigenvalues here are the same as some of the eigenvalues here. You get resonance type phenomena, and so that's another unpleasant thing that one has to deal with. And I want to simplify my life a little bit by saying I'm not going to go too high in the spectrum, and I'm not going to have to deal with these kinds of guys and resonances. And oh yeah, I should have said a bit more about the history. So in the porous medium regime, which is to say m bigger than 1 or p less than negative n, in one dimension, Angenet was able to give full asymptotics in 1988 for the nonlinear equation based on a linearization by Barenblatt and Zeldovich in 1952. And this was in one dimension. And in higher dimensions, Koch was, in his habilitation thesis, was able to sort of develop an invariant manifold theory for the porous medium equation. And he didn't have the explicit spectrum at his disposal, but he said, suppose that one can linearize this problem, then one can prove there exist invariant manifolds as follows. Okay. And for the fast diffusion equation, nothing, I think there's no, as far as I know, there are no results about asymptotics beyond like the second one. So what's the theorem? So first of all, I have to pick a threshold. I have to say how far into the spectrum do I want to look. And I can never go beyond this. But I also don't want to go past 2 times the lowest level. I want to avoid this kind of phenomenon. And so let me pick my, first of all, let me suppose that m is between m2 and 1. We can actually go down to m0, but the equation of results changes a bit, so I don't want to discuss them. And I want to choose a cutoff level in the spectrum, which it should be below the level of the continuous spectrum. And here we go. And above the level of the lowest eigenvalue, lambda 0, 1. So actually, but I also want it to be between lambda 0, 1 and lambda 2, 0, and 2 times lambda 0, 1. And right, like that. And I should say lambda 0, 1 is exactly the thing that leads to order 1 over tau. And lambda 1, 0 is exactly the thing that leads to order 1 over tau to the beta. So this has to do with the center, putting the center of mass at the origin kills this mode. And this mode here has to do with starting with the right dilation of the Barenblatt. So if I start with a dilation of this function, which is not exactly equal to the fixed point, it adjusts its variance to match that at the fixed point at this rate here. And so what else do I want to assume? I want to assume that the ratio between the initial condition and fixed point is bounded above and below. So let's say the log of this is bounded. And I don't know, not too much else. Right, I guess that's enough. So now what's the theorem? So the theorem is that you look at u of tx divided by the fixed point. Oh yes, I also want to assume that the fixed point and u0 have the same mass and the same center of mass. So that I have eliminated this mode here by fixing the center of mass to be the origin. And then, well, I already told you that I know that this quantity here tends to 0. And I told you I actually know that it tends to 0 at this rate here. But I can say more than that. I can say that if I subtract off a sum of things, and the sum of things looks like 1 over b plus x squared. And now I add all the eigenvalues up to this cutoff and the corresponding eigenfunctions. And the appropriate weights, e to the minus lambda LKT. Now I expect this thing to be small. And I expect it to be order e to the minus capital lambda t as t goes to infinity. And so these guys are actually polynomials of degree 2k, L plus 2k, I think. And so now I need to tell you what is the function space norm. And it turns out that you actually need, because these distributions have thick tails, and you actually can't control the tail behavior very well, the further you want to go into the spectrum, the more you need to suppress the behavior in the tails. So there's a weight on this space, and it depends on the choice of lambda that you want to make. So this is sort of similar to what Galilei and Wayne did in the context of decay of vortices in the Navier-Stokes equation to the Gaussian vortex. Except their way is much simpler because they're working in Hilbert space, and we're stuck in these finite spaces in order to have the analyticity results that we want. So actually, let me multiply. Let me put this factor over here because I'm more familiar. I'm more used to doing that. And now what's the weight? It's again, it's some power of the fixed point solution, e plus x squared. And what is the power? It's p plus 2 minus all of this over 4. And now I can put an L infinity norm on here if I want. So that's the theorem. And so I have to, what's to observe, the bigger you want to take lambda, the more strongly this weight suppresses information in the tails. And the other thing, so as I said, I simplified my life a little bit by restricting to capital lambda being less than 2 times the first non-zero mode. And, but even with this restriction, there can be up to 8 terms in this sum for certain choices of capital lambda and m. So this is, in some cases, this is the first 8 asymptotics. You can play some, I can get it up to maybe the first 11 or 13 asymptotics by playing, some more games. But I can get all the asymptotics, not even all the ones that lie below the continuous threshold. And we really don't, we haven't, it's an interesting question what happens when you get to the continuous threshold, and we haven't thought seriously about it. Okay. So, yeah.
Well, is there any reason for you to have continuous spectrum after some route?
Yeah, well, I can say the short answer to that question is that, so in the case of the heat equation, your eigenmodes are basically Hermite polynomials, and they're integrable against the Gaussian. They're square integrable against the Gaussian. Here you need your eigenmodes to be square integrable against this thing here. And your eigenfunctions are again polynomials. And you can't have too many polynomials that are square integrable against this. I mean, depending on how large or small p is. And so at some threshold, you can no longer have true eigenfunctions, and that's where the continuous spectrum starts. And there's another game you can play, which is very interesting. So I said, well, if you work in a weighted space, that affects the spectrum. And you can play with the weights. You can look at different bigger or smaller powers of this as your weight. And it turns out that no matter, so for a certain choice of power of the weight, this operator here is exactly a self-adjoint operator. So you're thinking about this as an operator on some space link, which has the structure of maybe a Sobolev space, W12 of Rn, with respect to weight UV. Now I can put a power here. So if the power is 1, this is a self-adjoint operator on the Hilbert space, and that's how we computed the spectrum. But if I put a different power here, this is no longer a self-adjoint operator, but it still acts on this thing, And the effect of making a non-self-adjoint operator is to expand the continuous spectrum. So in fact, the spectrum is no longer the original spectrum. It was a self-adjoint operator, so you had a bunch of bounding values, and then you had some continuous stuff. When you put a weight other than 1 here, what happens is you get a whole parabolic region in the complex plane that contains spectral information. Nevertheless, it's still useful to do this if you want to get this kind of convergence, right? And that's exactly the game we're playing down here. Other questions? Okay.
Can you repeat again what excludes the resonance of the modes to interact with the rest of the spectrum?
I said I don't go too high into the spectrum. So resonances occur when you have, like lambda 1 plus lambda 2 equals lambda 3.
Right.
But so the lambda 1 plus lambda, so I ordered things lambda 1 less than lambda 2. So the smallest thing that you could have like that is 2 times lambda 1. And so 2 times lambda 1 is here. I only look at eigenvalues that are below 2 times lambda 1. And nevertheless, I say in some cases there are 8 modes below 2 times lambda 1. Otherwise, we would have to develop an invariant manifold theorem for this equation, and that we weren't up for that. I mean, in principle, it could be possible to do it, but we didn't do it, or we haven't done it yet. This was hard enough. Yeah, actually L infinity, of course, is, so I said you can put L infinity here, but in real life it's not such a convenient space to work in, and particularly if you want the smoothest kind of result, then you have to work in a Holder space. And so I say you can actually put a stronger norm here if you want. You can put CK alpha, or let's just say C alpha of Rn. But unfortunately not Rn with the Euclidean metric, Rn with a metric that's adapted to the problem. So if I linearize this evolution around this fixed point, then what I get is something like and of course the linear term sticks around. And if you plug in this form of u beta to this expression here, then what you have is divergence of u plus x squared, radiant u minus u beta. And now it looks like the diffusion speed is blowing up at infinity, and that's a problem. And but on the other hand, this thing here is exactly the Laplace-Beltrami operator for a certain Riemannian metric on Rn, which is conformally equivalent to the flat one. And so this is the Riemannian metric that I want, and it turns out that mg is Rn with the Euclidean metric divided by u plus x squared. So this is, in 2 dimensions, that would be known as the cigar manifold. And the effect of using this cigar geometry has the effect of taking an evolution that was degenerate parabolic and making it uniformly parabolic in the new geometry. And now you get the smoothest results that you wanted by using the Georgi-Nash stuff. Okay. So so it's now uniform parabolicity. And so the smoothest result that we actually use is that we now have, if I take U naught in a Holder space on this manifold, and I map that to the solution, UT, which now lives in a Holder space. Actually, we can do CK alpha, yes. Time cost that's manifold. That this map from the initial condition to the solution is smooth. So that's the theorem that allows us to do this linearization. Okay, so I have a few minutes left. So what else can I say? I can say we can actually, yeah, I can talk about the geometry of the first few modes. So the geometry of the first few modes actually looks the following way. At the heat equation, the spectrum consists of the integers, and there's no continuous spectrum. And well, you have this continuous spectrum here that looks sort of as follows. And you have an eigenvalue like this, and another eigenvalue like this, and then you have an eigenvalue like that. And so this is the guy that corresponds to translations, lambda 1, 0. And this is lambda 2, 0, and this is lambda 0, 1 here. So I already sort of told you what is the invariant manifold for this guy. Slow manifolds. The one corresponding to this guy is the set of all translations of the Baron-Blatt. And the one corresponding to this guy is the set of all dilations of the Baron-Blatt. And I can also tell you what this invariant manifold is, which is, I mean, again, depending on whether you're in the porous medium or the fast diffusion regime, it's the second or the third eigenvalue. It consists precisely of the affine images of the Baron-Blatt. And so we actually know the first several modes more or less explicitly, and you can say what the dynamics on those manifolds are by solving ODEs. And I guess I can say, since I have like 1 or 2 minutes left, I can say a tiny bit about Joel's question, which was, how does the linearization look? And this is also related to the remark I made to Kiam. Well, okay, so if I take V to be the ratio between U and U Baron-Blatt, and V bar to be V minus 1, then I have dV bar dt is some linear operator acting on V bar. And the game, as I was mentioning, the game we play is we play this game of conjugating this linear operator by different weights. The weights appear here. And so let L eta be cosh minus eta s composed with L, composed with cosh eta, where S is exactly S is cinch inverse of absolute X. So S is exactly the geodesic distance to the origin on the cigar. And, well, I mean, I don't want to write out the details of this operator, but this operator looks more or less like a Laplacian. Let me say something like, maybe I lie slightly, but it's really at infinity it looks like this. And then there's a potential term, so it's like a Schrödinger operator. And the potential has a universal form. It's basically like some constant depending on P and N over cosh square root of S plus another constant depending on P and N. And then there's a transport term. Which spoils the self-adjointness of this operator. But the point is, by choosing eta to be a particular value, P over 2 minus 1, you kill this term, and then you have the self-adjoint operator that you diagonalize. And the fact that this thing has a universal form here, depending only on P and constants depending only on P and N, is telling us that the problem is what allows the problem to be special enough to actually find the eigenfunctions in terms of what do you call them? Hypergeometric functions. All right, thank you very much.
Any questions or comments?